recording. We are recording now. Very important information here. Very, very important. I sound like Trump. Very, very important. It's amazing. It's the greatest information you've ever seen. And what we've been studying are applications of the derivative. The last two classes we did optimization. And today we are going to take the tangent line and think of it slightly differently. And when we think of the tangent line slightly differently, we're going to call it the linear approximation. Okay, so why do we call it the linear approximation? Well, let's look at this. Why is it called that? Let's look at an example, and we'll see sort of what's happening here. Example. Let's say f of x equals e to the x. F prime of x equals e to the x. And let's determine the linear approximation at 0, 1. So we know that L of x equals f of 0 plus f prime evaluated at 0 times x minus 0. And if I plug those in, I get L of x equals 1 plus 1 times x minus 0, which of course, if we write it like a normal human being, would be 1 plus x. So let's put a little red cloud around it because it's so beautiful. I love it. Do you love it? How are we doing? Does anybody have a question about this? Now, here's what you'd like to do. What is useful about this? Well, if you draw a picture, what you'll notice, and what I'd like you to think in your mind before we do anything is remind yourselves that we're on this big sort of thing called Earth, right? And I don't know, I'm hoping that you guys all trust that it's not flat, as you know, that it's this sort of spherical like object. Maybe not, I don't know, maybe I'm a fool. But let's assume that we all agree with the model that most people believe in, that we're on this big globe. And even though it's curved, our size relative to the Earth is that we don't see the curvature of it, right? You know, you don't look out there and say, woo, right? You don't think of it that way. You think of it as being flat. And when I walk, you know, I go, I'm walking on flat ground, correct? And so my size being so small relative to the Earth is that we can think of, you know, the sphere as being made up of very, like lots and lots and lots of small flat things. Just like you can imagine any curve, and I've showed you this before with the circle, right? That you can imagine any curve can really be visualized as lots and lots of straight lines. Remember, we did this a few times during the semester. We went to Desmos and I showed you a polygon with like 60 sides. And I said, there ain't no way in hell you don't realize that that's not a circle, right? Now, if you zoomed in on it real small, you say, okay, maybe that ain't a circle. And then also don't forget that anytime you play a video game or watch a movie, you have all these little pixels on the screen. They're not curved, but their size relative to you is so small that they can confuse you to looking curved. Anyhow, I don't want to keep getting into that, but here's the fact of the matter. If I go to the next page and I draw this, so here's my X and Y axis. And so if I draw e to the x looks like this. It's this asymptote. That was bad. Let me draw it a little prettier. So this is my function y equals or e to the x. And we know, hopefully you guys all are aware, that it goes through the point 0, 1. And then the tangent line is the line that has slope 1. So this is the tangent line, y equals 1 plus x. And we gave names to these things. Don't forget, this is, even though I'm writing it like that, we called this L. And of course, we called this guy F. And so here's the key idea. If x is approximately 0, we would expect 1 plus x to be approximately the same as e to the x. So what I'm going to do, since it's much clearer to use technology to convince us of this, imagine you took a microscope and you zoomed in around this point, 0, 1. What's going to happen? Well, let's go to Desmos and check it out. Our old friend Desmos. So I'm going to first graph my function, which is e to the x. And there it is. We'll make it nice and fat so we can see it. And then we'll graph our function L. 1 plus x, there's our line. And see, what I want you to do is if you zoom in on this point 0, 1, what you'll notice is that the blue and red are basically on top of each other, right in here. Now, of course, if I move down here, I see a huge gap, not good. But over here, I mean, over here, x would be -1 or -1.3. But what I'm talking about is when my x values are near 0, when I'm right in here on the x-axis, my outputs are close together on the red and blue. Can even zoom in more. And the more I zoom in, the more what I'll notice is that the blue and red start to look like the same thing. Because anytime I have a curve, the more I zoom in on that curve, the more straight it starts to look. Again, anytime I zoom in on a curve, draw any curve you want. I don't care. Go take a magnifying glass and look in on one small piece or put that curve under a microscope. The more you zoom in on it, the more and more straight it's going to look. And if you're not convinced in that, you can compute some actual values. Make a table. Let's pick numbers that are close to 0. Suppose I pick -0.05 or 0.01. Look at the outputs here. Now, let's make a table for our linear approximation, -0.05. Looks like a pretty good approximation to me, accurate to 2 decimal places. Pick 0.01. Once again, accurate to 2 decimal places. Get even closer to 0. If I get even closer to 0, how about 0.005? Or 0.005. Once again, now I'm accurate to 3 decimal places. And over here on the right, you'll see the corresponding outputs. Look, the red dot is basically, for all intents and purposes, on top of the blue dot. So by the way, and I don't want to get too far into this, but I want to say two things. First off, does anybody have a comment or a question? Okay, so one thing to think of that you might say, well, who cares? Well, imagine you didn't have calculators, which was the case 50, 60 years ago. How would you tell me what e to the 0.05 was? Would you know how to compute that? Here's one way you could have. Most people would be happy with 2 decimal places of accuracy, would they not? Now, another thing you might say, well, you might say, oh, Grady, this stinks. I mean, it's not a good approximation once you get over here. It's terrible. And I say, you're right, but guess what? Take Calc 2 and you learn that you can do better, because if I do this, and instead I use a quadratic, now I'm even better. Look how good it is up here. And then and you'll learn where these numbers come from. And then if I add another term, now I'm even better. The red disappeared. Cool freaking fact is we can take e and approximate it by a polynomial of any degree we wanted. Now, why is that cool? What would you rather differentiate, polynomials or other things? You guys love polynomials. You never mess that up. As soon as I give you sines and cosines and exponentials, guess what you do? Mess them up. So this idea of approximating a curve by a line is important, and it's the first step in a much bigger thing that you learn about in calculus 2. Does anybody have a comment or question about this? By the way, physicists do this all the time. Engineers, they approximate all the time. There's a name for this, by the way, if you're curious. It's called Taylor polynomials. You'll learn about them in physics if you take physics. Well, you'll learn about them in calculus too. They use them in physics all the time. Engineering. Okay, so back to our notes. That is how we can think about sort of the geometric interpretation of this. So in general, though, and this is what you want to take. This is not just for the example, but in general, if x is approximately a, then the function outputs can be approximated by the linear function. So this is an important fact. Now, of course, you might nitpick. You could say, well, what does approximately a mean? Well, of course, we didn't really get into that. That's a whole different analysis. And that's going to depend on how sharp the curve is. Another consequence of this, and this is how sometimes people describe curves that are differentiable, is we say they're locally linear. And that means any curve you have, you can think of it as being built by a bunch of straight lines. When I was in 8th grade, I had this very cool, I don't know if he's cool. His name, this very good teacher, an algebra teacher in 8th grade. His name was Mr. Loser. And I don't remember if I told you about him or not. He was crazy. He's one of those guys that always wore like a short sleeve dress shirt with a tie. Looked like he was like stuck in the 1950s. That's how people look. In my mind, that's what like middle class men dressed like in the 50s. But anyhow, he made us come at his desk every class, and we would take notes right in front of him and stand up. And he was a great teacher. He was scary, but I'll never forget. It was May 15th in like 1992. He said, I thought that day. He was all proud of me because I answered a question correct. Can you believe that? He was mocking me, and here I am. But anyhow, he was a great teacher. And he made us do this cool thing. And I forget what it's called. Let me see if I can find it on the internet. I know I can find it. So let me go back to the internet. Let me get a new web page. I think this is it right here. Yeah, this is it. So what we did is we did these things where you can create curves using straight lines. And this is exactly the idea we're saying. And this is kind of like where art and math, one area where they intersect, can make these crazy, awesome patterns. So here's what we did. This is a very good example of what we did. This looks like a hyperbola. So what we did is we all had these pieces, these blocks of wood. And then we went home and he gave us nails, and we nailed nails in, and we took yarn and we attached one nail to another nail with string, and they were all straight lines. But when you did them in a certain pattern, what it did is it created a parabola. It was really, really, really cool. And so it's these kind of ideas right here. And so, oh yeah, this is exactly what it was, only we used yarn instead. So you can see what you're doing is you're using straight lines, and then at the end of the day, you get a parabola. It's pretty cool. So again, this is really the big theme of even how I've said this numerous times. You're probably sick and tired of me friggin' saying it, but this is sort of the essence of how movies work, film works. You have these still pictures that are moving rapidly, and they're confusing your mind into thinking that something's actually moving. Right? It's a good mind F in a good way. And here is sort of the mathematics behind that. It's pretty cool. Anyhow, you can make all kinds of pretty awesome things. Now, my kids, she has this thing. It's like a spiral graph, which is a similar thing. You move these pens around in these different ways and get all these pretty pictures. Math meets art. Beautiful. Ain't that something? Look at this. These are all straight lines, but it all looks like curves, right? What a time to be alive. What the hell are you guys going to do without me in your life for like 2 months? Is anybody, you guys taking calculus too? Hopefully. Are you taking it? Why not? What's your major? Okay, you should take it anyhow. Yeah, because you should take lots of math and stats. You'll have any job opportunity you want. I'm telling you, you let O'Grady run your path. You'll be rich and not necessarily rich and famous, but you'll be successful. You should always mix, no matter what your major is, you should mix it with two things, math and computers. It's 2020. You got to be able to use computers, and you got to understand math, and then you'll be famous. What's everybody yapping about on the chat? There you go. Stats. That's exactly right. You should take stats too. Carly, yeah, but we already had your discussion. We got to figure your situation out. It's a travesty what's happening. Authorities are being jabronis. You know, they finally put the jabroni in the dictionary now. Everybody thinks that it's like some bad word. It's not. I think it's an Italian word that suggests you're an idiot. But the great Rock, you know, the actor now, but when he was a famous wrestler, he always called people jabronis. And that's what the Rock is cooking. Okay, anyhow, you should all take lots of math stats. Think about how poor we are as citizens because we suck at statistics. Not to get off track, but it's worth pointing out, and I don't want to get on politics, but if you paid attention last week, one of the big things from the Republicans is they're all like sending this screenshot of like what they claim is cheating in Michigan because they said that the Democrats just dumped votes on them overnight, right? And then they have this stupid picture, which is not the correct one. And it's people's lack of like even just basic statistics that allow them to get on this rabbit hole where this graph is lying to them. And if you actually look at the actual data, the data suggests that there was not just a Democratic jump overnight as was expected, but there was also a Republican jump overnight. It's just no one zoomed in on the data to see that. And it turns out the Democrats was a bigger jump. But anyhow, most people, I think that's one of the problems I think with a lot of us is we don't have number sense. We don't have any grasp on basic, what I would say, statistics. And these ideas of causation and correlation, what do they mean? How do they differ? Does one imply the other? And all that stuff. I think the world would be a better place. I often go back. I wish they would force high school kids to take classes and that stuff, but they don't. We're still stuck in this world where they want to force you through algebra for 4 years. And then you don't take it for 4 years. You take a senior year off, and then they make you take it in college, and then you have to take calculus, and you're mad because you forgot everything. That's what happens. I always say you should invent a time machine and go back to your high school counselors who told you don't need 4 years of math. And you say, damn you, you ruined it for me. Says the biased math professor. Of course, to build your time machine, you'd have to be really good at math, but then that would require that you're really good things that you're not really good at. So again, we're kind of like in an endless circle. Okay, so again, if we come back to this beautiful thing of linear approximation, it's foreshadowing something you'll study next semester, but you should know how to do it. And we don't need to do too many examples right now because you already know what it is. It's the tangent line. We're saying, okay, you can use this now to approximate values that otherwise you could not necessarily get. So let's do one example real quick. Suppose we want to know the cubed root of, say, I don't know, how about 65? Suppose it's 1912. You have no calculator. Did you ever have teachers that said you can't use calculators in case one day you don't have one? They ever tell you that dumb lie, like all of a sudden all the technology is going to disappear and you're going to have to do arithmetic by hand? I don't know. Anyhow, let's suppose, here's a very basic, and by the way, let me point this out because I'm not going to be that person that's going to lie to you. Ain't no friggin' working engineer doing this to compute the square root of 65, right? That's not the point right here. Here's what the point is. We are teaching you what we call elementary approximation techniques. Just in case later on in life, you have to learn more sophisticated approximation techniques. Like this is sort of like the first step in understanding what we're doing here. So, you know, you can't do fancy analyzing of functions and data if you can't do it with basic things you can represent simply on Desmos. And I've tried to explain that to you before, but, you know, I don't know if it gets through to you. All right. So anyhow, let's determine the linear approximation of f of x equals the cubed root of x. And I'm going to do it at the point 64, 4. Now, am I pulling these numbers out of my you know what? No, I'm not. Think about it for a second. And then use this to approximate the cubed root of 65. Now, where did I get the number 64 from? Well, okay, so I said, let's imagine we wanted to approximate the cubed root of 65. I would imagine in my head it's somewhere a little bigger than 4 because I know the cubed root of 64 is what? Well, 4 cubed is 64. So I know the cubed root of 64 is 4. So I'm going to take a cubed root I know, that being the cubed root of 64, and use that knowledge to determine something about the cubed root of a number that's close that I don't know. Right? Now, I'm not saying this is the only way you can do it, but this is one way you can do it. So, here we go. So, solution. So we know the first step is we have to compute the derivative. What's the derivative of the cubed root? Well, it's 1/3 x. Now, if the power of the cubed root is 1/3 and I subtract 1, I get negative 2/3. So since that derivative is that, we have f prime evaluated at 64 is, I'm going to write this a little differently so we can sort of get at it. This is 1/3, and then it's 64 to the 2/3, which is 1/3 times. There's two ways I can evaluate 64 to the 2/3. I can think of it as 4 squared, or I can think of it as 64 squared, then take the cube root. So one of those is a little easier than the other. So I'm going to take the cubed root of 64. So that gives me 4. So this is 4 squared. And at the end of the day, this becomes 1 over 3 times 16, which happens to be 64. Does anybody have a question about this? All right, so what's the linear approximation then? Thus, the linear approximation is f of a, so let's just write, or excuse me, f of 64 plus f prime of 64, and then that's times x minus 64. And that's going to simplify to 4 plus 1 divided by 64 times x minus 64. So that's the linear approximation. You could simplify that if you wanted, but so maybe we'll just clean that up on the next page. Does anybody have a comment or a question on our math here? All right, so if we rewrite that, I'm not saying you have to, but we could rearrange or rewrite as L of x equals 4 plus 1 over 64 times x minus 1, which of course is the same thing as L of x equals 3 plus 1 over 64x. So this is the linear approximation. Now, this is what we were asked to do at first, but we can use this to get information. And so the beauty, the geometric sort of consequence of this is that the graphs are close together. So what we get is, so for x close to 64, whatever that means, we get 3 plus 1 over 64x should be approximately the cubed root of x. So if x is equal to 65, the cubed root of 65 should be approximately 3 plus 65 over 64. Which, if we wanted, we could determine that fraction straightforward. So, I mean, if you straightforward, I mean, write it in fraction notation. So if you find a common denominator, I'm not suggesting you have to do it, but I like to do it the old-fashioned way. And that is find a common denominator and add. So 64 times 3, and what you end up getting is you get 257 over 64. And this is equal to 4.015. 625. So we can compare with a more accurate if we use a calculator. So if I go to a calculator, what's the square root of 65? So I'm going to take the square root of, excuse me, not square root, cubed root. So the actual value, or using a calculator, says the cube root of 65 is approximately 4.0207. So we are accurate to 1 decimal place, but if we round using the regular convention, we're accurate to 2 spaces. Why did I write 36? This is 65. Did I have? It was like, it's like my mind is losing itself. Comments, questions? Now, am I suggesting this is how you should compute cube roots? No. Because this, and the only reason this example worked, I shouldn't say the only reason, but if I asked you to do the cubed root of something like 50, then it'd be a little more difficult, because is there a number whose cubed root is known that's near 50? Well, you'd have to probably use 64 again. And are they close enough that there's an accuracy issue? You don't know. But again, the idea is that we can approximate curves with straight lines. And by the way, this is, if you look at the graph, and it's worth doing this. If I go and graph these creatures, f of x equals the cubed root, which I'll write as x to the 1/3. There's the cube root. I mean, it already looks pretty straight over here. And that's not going to shock us when we go and we put L of x, which was 3 plus 1 divided by 64x. And so it looks bad here, but if you look at that line, if you start getting out here towards what's happening at the point we're interested in, which is 64, when you move out here, you see that the green and purple look pretty close now, do they not? And that's if we didn't make an error. Did we make an error? So here's an interesting thing to think about. Let's come out here. So notice the green line. Something happens out here that we should be paying attention to. So if I put the point 64, 4, one of the things that we note here that should be concerning to us is the purple line is our tangent line. And if we look over here, it seems to be, at least according to Desmos, the purple line seems to be above the green curve. However, when we go to the other side, it looks as if they switch. And now the green curve is above the purple line. That should be concerning to us. And let me explain why, or it should be concerning to us. because it makes us think we have a mistake. Why do I think that we have a mistake? Well, if I think of my calculus, I'd look at the derivative. Now, if I take the second derivative becomes -2/9 x to something. And that means the second derivative for this function is negative. And a negative second derivative tells me my function is concave down. Well, if the function is concave down, that means the tangent line should always be above the curve. So we have a discrepancy here. Something is not correct. Let me state this again. The tangent line we found, at least when we graphed it, seems to not be tangent at the point. Now, maybe Desmos is sort of lying to us, or more likely, we made a mistake. Now, the question is, where is our mistake? Very, very good. So if you come back, notice here, this is 4 squared, which is 16. 16 times 3 ain't 64. What is 16 times 3? 16 times 2 is 32. So another 16 makes it, as we just saw, 48. So, bad news. And so that makes this bad. And of course, even though we got an answer that seems reasonable, that makes this bad. We understand what I'm saying here? So look, I think it's important that you do this when you're solving problems. Ask yourself, does the answer make sense? Now, here's a great example of where the answer you get does make sense. You wouldn't feel like you made an error. But we did make an error. In the way that I am trying, well, I shouldn't say that. I mean, technically I made the error on purpose, but the way that I would hope when you're doing work, trying to learn, is that when you go to verify something using technology, like looking at the graph, if something doesn't add up, well, then you need to think about what you did. So let's get our correct reasoning in here. And the correct reasoning is as follows. That is f prime of x, as we know, is 1/3 x to the -2/3. And so f prime evaluated at 64, if you do the arithmetic, it becomes 1/48. Thus, L of x is 4, like we thought before, plus 1/48 times x minus 64. Since L of 65 is approximately the cubed root of 65, oops. We can reason that this is 4 plus 1/48. Now, if I plug 65 in there, that's just times 1. And then that is approximately the cubed root of 65. And if you do the arithmetic here, the left-hand side, well, let me write it like this. So since this is the case, what do we have? We have and this is equivalent to 193 over 48, which is equivalent, if you put it in decimal notation, 4.02083. And now if we take what the calculator gives us, which we had from the previous page, 4.0207. You'll see that our approximation is actually better than we got from the wrong one, and it's actually more indicative of what it should be. We should expect our approximation to be an overestimate because the actual curve is concave down, which means the tangent line has to be above it. There's a lot of little nuances here that I'm trying to point out, and I hope that there's things that you'll consider. Well, then again, I actually hope that you'll just care, even for a little bit. Maybe you will, maybe you won't. So the reason I do this example is because we made a slight, tiny arithmetic error. And with our little arithmetic error, we got the wrong answer, even though the answer we got tended to look correct. It didn't look like we were wrong. And attention to detail, it's very, very, very important. So, you know, I hope you'll consider that when you're doing this stuff. Or maybe you won't. I have no idea. All right, does anybody have a question or a comment about this? Going once, going twice. All right. Okay. So what we'll do is we'll stop here, and then we will start with new stuff on Thursday. Good place to start. So your next homework that I'm going to post today is going to, for lack of a better word, you're going to hate it. It's a bunch of those optimization problems and a couple of these. So it's going to seem hard and difficult, but you should work through them. And then ask questions if you can do it. We've done what, 4 or 5 examples of those optimization ones. So hopefully you can suffer through the time that it takes. All right, guys, thank you very much. I hope you'll study this example. I think it's important to analyze errors, and when you make errors, you got to remember you're not always going to get things correct. And that's the best. You got to learn from when you make mistakes. All right, everybody, thank you very much. I will talk to you soon. Very good.